look at a method used in a method used in mathematical modeling. So in modeling, we are trying to simulate real life situations using mathematics. For example, growth of a population, or perhaps how an object accelerates as it falls, or how an object heats up, or maybe how much something grows with respect to different stimulus, how an infection spreads, things like that. And usually when we're studying these, we're studying differential equations. So that's where the equations are written in terms of the rates of change of things. So for example, we could say an equation like the rate of change of population is proportional to the population, by which I mean number of people that are already there. So if there's more people, the population will change faster because more people are having babies potentially. So we can write this in shorthand, basically like this. Okay, in which this stands for the rate of change of population. That's what this dot represents as change over time. And this is the population now. And this constant is the constant of proportionality, which is sometimes called the growth constant. So we want to solve, what we want to do, because we can't solve it right away, so what we want to do is we want to find what a potential solution would look like. So here's how we do it. So first of all, we make a unit of population. So let's call this unit P, for people, for example. And because this is the rate of change of the number of people over time, we also need a unit for time. Let's call it capital T. And these so what we want to do is use something called dimensional analysis, in which we assign, for example, the population and time with a dimension represented by capital letters here. So these dimensions are like different from the dimensions in 3D space, for example. And the reason we introduce this is, first of all, we have this idea which seems to work, and it's actually kind of intuitive that it would work. So it's a sort of axiom that things with different units, for example length and time, cannot be added together. And if we want to use any sort of, if we want to apply some sort of mathematical operation to them, then to do it, for example raising to a power, to do so you would have to ensure that not any mathematical operation. For example, operations which involve summing powers of things. So, For example, if you want to exponentiate something with units, you can't. It wouldn't really make sense. For example, if you wanted to do e to the 10 newtons, then if you know the Taylor series for e, then you get e times 10n plus 10n squared over 2 factorial and so on. However, the problem is this is newtons squared over here, and this is newtons, and this is like no units, so they can't be added. So you can't exponentiate with units. So that kind of puts a restriction on what the solution can look like, and we want to see what kind of solution the population can have. So to do so, let's first of all, let's just see what the units for alpha is. So because population has units of capital P, so the units on this side is capital P and capital T to the minus 1, and over here there's capital P again. So that means the units for alpha is capital T to the minus 1. Okay, so the next step is to notice that the units for T is the same as units of 1 over alpha. So now what we can do is now we want to construct a function that describes the population entirely, everything that the population could possibly depend on. So it could depend on alpha, it could depend on the starting population, because if you start off with more, you'll have more by a certain time. It could also depend, in fact it probably will also depend on the time, and it depends on nothing else. So it depends on the rate, the growth constant, initial population, and time. I'll put a little colon in front of time because usually this is the only value that we're looking at actually change. Okay, so what we want to do now is we want to I use the term normalize in the same way you would normalize a vector, kind of, but we don't want to normalize the dimensions, to just remove the dimensions from the problem. So over here we have a dimension of P. So what we want to do is we want to divide through by something, in this case P0, to remove the dimensions. And we'll call this P with a little tilde on top of it, I think. And we want to create a new function called psi tilde. But instead of taking these values that have units, we're going to normalize all of them so that they don't have units. So in the case of alpha, we're going to divide by alpha and we'll get 1. In the case of population, we're also going to divide through by population to get 1. But in the case of time, because we've noticed that time has the same units as 1 over alpha, we're going to divide time by 1 over alpha. Okay, now you notice that psi tilde only actually depends on this one variable. Or you could alternatively write it this way, alpha t. And so you see that the population must have the population must have a function or a solution to the population differential equation must have a solution of the form P naught times psi tilde alpha to the t, where psi tilde is some function. And we can now go on to use other standard techniques to prove what it is. But what this does is it points in the right direction of what kind of solution you're looking for. The actual solution, turns out, is P naught e to the alpha t. But our dimensional analysis showed us that the alpha and t have to come together in the solution. Also notice that it showed us that this population parameter had to divide through on the other side in order to make our to cancel out our units, so it had to be multiplied to whatever solution we had at the end. So that's just an introduction to dimensional analysis. Thanks for watching.